So in your regular maths, you should have already covered perfect square and probably difference of two squares as well. I got a few shakes of the head though when I said this yesterday. It might be because you can't remember. So this is going to be just a slight, hey, remember what you did in class a little bit, but I'm going to use more complex examples to try and bring out some of this stuff. So bear with me if it feels a little bit slow, and I apologize if I'm going too quickly, but it's been recorded. You can go back and have a look. So you can see there's the two success criteria here. Can you do this? Will you be able to do this? This is what success looks like. You can identify and use the perfect square rule to expand. You can identify and use the difference of two square rule to expand. So we're going to look at both of those in each of those in turn. And I think it's really important to just point out there that word there is kind of like at the heart of it. Identify. Ultimately, you want to be at the point where if you see a problem, you're asking yourself, does it fit a particular rule? Now, on Monday, we talked a lot about, I talked a lot about the idea of this toolkit that you have and that you're pulling out a tool. And at the moment, based upon Monday's work, yes, we looked at more complicated examples, but effectively we did basic expansion work and collecting like terms. And they were the tools that we used. But now we're going to add two more tools that will allow us to work efficiently with, in our case, expansions. So that's what the perfect square rule and the difference of two square rule does for us. It gives us more efficient methods for expanding, and later on, and the bulk of this course is on factorization. So here's the perfect square rule. You might not have seen it quite written like this before in the red there, but nevertheless, that's just an efficient way of writing the rule. Feel free to write these down if you don't have them already in your summary book. I will very briefly explain how the rules work later on, but they are the rules. What you need to get good at is recognizing when an expression you have in front of you fits that rule, because it won't always look as simple as that. It won't simply be a variable plus or minus another variable, and then there's a big square sign around the whole thing. It won't always look like that. A good math student will be able to select the right tool for the purpose, and in order to select the right tool, that math student needs to be able to identify the kind of problem. Okay? So if you want to take the analogy back to a tradie like I did yesterday, if the tradie sees a screw halfway into a piece of wood and then pulls out a hammer to bang it into the wood, that will work, but it's not the right tool for the job, right? Same with this. If you see a plus b all squared in some format and you instead do a big long expansion to get it to work, it will work, but it's a pretty untidy way of doing it. And it means that you're losing efficiency, you're taking more time to solve problems. Okay, so there's the two rules there. A plus b all squared equals a squared. So we square the first term in whatever it looks like. We then mush these two terms together and double it. That gives me my 2ab. And then I square the second term, and that gets me my b squared. If it's a minus b all squared, notice there's only one difference, and that's the minus in the middle. So the operation here, plus or minus, follows through to the middle term of the expansion. So a minus b all squared, square the first term, mush them together and double it, but subtract in this instance, and then you still add the b squared term. Okay? A fancier way of writing it is to go a plus or minus b squared equals a squared plus or minus 2ab plus b squared. Is that hand up, Will? No, cool. All right. Anyone got any questions over that before I go through a really straightforward example? Okay. Again, I know I'm not doing anything too amazing yet. So we've got 3 minus x all squared. And so I'll spell it out. You can do it in one go, really, but I'm going to spell it out so that we can sort of see it. We've got 3 squared. That's the first term. Now it's a minus in the middle, so it's going to be a minus here. Mush them together. 3 times x is 3x. and double it, and then plus the square of the second term. And now I'll just write it out. Now that's just the middle line there, you don't really have to do. So it's 9 minus 6x plus x squared. Any questions? Okay. Think about this one. If you're watching this back on video, then pause and think. Will the middle term always be even? Yep, nope, yep. Okay, I promise you, you will not get any sort of electric shock if you get it wrong. So I'm going to do what I call sometimes a straw poll, which is simply you raise your hand for one or the other, vote for one or the other. This is not democracy. Mathematics does not work on the most popular vote for something. This is just to get a sense of what you think. So try not to look around for your own sort of, trying to be in with the bigger crowd. Who thinks, yes, it will always be even? Still have people looking around. Okay, who thinks it will not always be even? It could sometimes be odd. Okay, hands down. The majority said it should be even. The minority said that it should be odd. The gutless didn't put their hand up. And yes, I know who you are, so I looked around. I know it's really challenging to sort of, is it going to be even or odd? But nevertheless, maybe try and break through that sort of absolute shame of possibly getting something wrong, because it's okay. It's just a bit of maths. That's going to work really well, that rant for the video, isn't it? The people, anyone who's not here is going to be watching it and going, what happened in that classroom? So the majority have it wrong. The minority had it right. It could be odd. It's just that you need to recognize that in order to get this to be an odd number, for example, I would have to have, I don't know, a fraction. So if instead of 3 minus x, if I had 1.5 minus x, what's 2 times 1.5? 3, which is odd, right? So the problem with our thinking is that we often think whole numbers all the time, and that causes us to automatically assume stuff like, oh, it's got to be even in the middle, doesn't it? Because it's twice something in the middle, so it's got to be even, because twice something is always even. No, twice a whole number is always even, but twice a fraction can be odd. So that's what I mean by identify. If you get into the habit of saying, oh, well, it's 3x in the middle, so it couldn't possibly be a perfect square, then you might have missed a trick. See what I mean? Okay, I won't harp on about it. There you go. So there's the example there. I'll zoom up on slide 4 and then I'll go show you all of them at once there. But this is what I mean by identifying. Each of those equations there may or may not be a perfect square. Looking at the first one, you may be given a perfect square in this format here that I'm circling, x plus y times x plus y. It is still a perfect square, right? Because if I multiply anything by itself, then it's just the square. So 2 times 2 is 2 squared. 9 times 9 is 9 squared. Pi times pi is pi squared. Now, x plus y is just a number. We don't know what it is because x and y are unknowns. They may be the same number. They may be different numbers. X might be a fraction. Y might be pi. It doesn't matter. Ultimately, x and y are just numbers. And when you add them together, you get the sum of those two numbers, the result. So we're just saying one number multiplied by the same number must be a square. So x plus y times x plus y is x plus y squared. So that is a perfect square. Sorry, yeah, it's a perfect square problem. What about the next one? Is it a perfect square? I'm seeing a few shakes of head. No, it's not a perfect square, but then we're going to have to add something to that yet. So is it a perfect square? No, but will I be using perfect square to solve this? Yes, and I'll explain why. Have a look at that first expression there, 2x plus 6. Who can tell me something about that expression? Both of those numbers are even, and therefore Right. Or I know we haven't done factorizations yet, but I know that for the last couple of years you do know how to factorize at least fundamental stuff. I can divide by 2, or more importantly, I can take out a common factor of 2. So I'll just do it in blue just so it stands out a bit. So I can go 2 outside of, and what would be on the inside then? 2 times what equals 2x? Just call it out. Don't even put your hand up. No, 2 times 1 is 2. 2 times what equals 2x? X. 2 times what equals 6? So what have I got then? I've got 2 times x plus 3 times x plus 3. So I've got that repeated factor again of x plus 3 now that I've taken out the common factor, and now I'll use perfect square. So although it doesn't start off as a perfect square problem straight away, if you can look at it and go, oh, if I take out a common factor of 2, I will be left with a perfect square. So building up this ability to identify perfect squares is really important. What about this next one? You've got to be careful. Negative x minus 3 multiplied by x plus 3. Number one, it is not a perfect square, is it? Because I don't have this term, although it looks the same, this is negative x and this is positive x here. Although it looks the same, I've got a 3 and a 3 here, I've got a minus and a plus here. So it definitely does not fit the perfect square. But it can be changed into a perfect square. So I'll do that again. In this case, I'm going to take out a negative outside the brackets of the first one. So negative just simply means negative 1. Negative 1 times what will give me negative x? Call it out, x. Negative 1 times what will give me negative 3? Positive 3. So I've got negative, and then effectively inside the brackets, I've changed the signs from minus and minus to positive and positive. That's what taking a negative outside the bracket does, right? It swaps the signs on the inside. And then I've got x plus 3, which of course is x plus 3 all squared. I'm being a bit squishy here. So negative x plus 3 all squared. So to do this problem, I would expand the x plus 3 all squared. I get x squared plus 6x plus 9. And then I'd put the negative inside the bracket to get negative x squared minus 6x minus 9. Okay? Is that all making sense? All right. I'm going to zoom up a little bit more so that we can sort of see it again. You're probably getting the sense of it now that these are all pretty much all perfect squares. This one's a bit more straightforward, right? 2x squared plus 1 times 2x squared plus 1. It doesn't matter what the two terms are. They can be complicated terms by themselves, but as long as we've got something which fits the role of a, and what does a equal in this? 2x squared. Don't be put off by a square. It's just a term. So 2x squared, and b is, of course, just 1. So we do have a perfect square, even though it might not look like it. This next one is a little bit more tricky to see. It's x plus y plus z. I do my z's like that, sorry, but that's a z. X plus y plus z all squared. Now, again, traditionally, it does not fit the pattern of a perfect square because a perfect square expansion requires 2 terms. How many terms have I got there? Starts with 3 and ends and rhymes with b. So it doesn't quite fit the perfect square notation. But in mathematics, we can work efficiently by applying tiny tricks like this. Let a equal x plus y. So wherever there's an x plus y in the expression, I'm going to replace it with an a. Now I've got a plus z all squared. Now I can expand that using a perfect square, and that'll give me a squared plus 2az plus z squared. Then I can replace the a with the x plus y, and then I can do more. So there's actually quite a bit of expansion work there. But with efficient usage of the perfect square rule, it is still going to be easier. I'm going to zoom out so you can see the whole thing now. It's still going to be easier than doing it by longhand, which is like using a 3x3 grid box method. Make sense? Okay. Very briefly, that's why it works. when you use the box method, you'll always have an a squared to start with because you're multiplying a by a. You'll always have a b squared to end with because you've got a b times b. And these will always be an ab because of that'll be a times b and that's b times a. So you end up with an ab and ab, which is why you get twice in the middle. And similarly with a minus b all squared. I won't spend any time on that other than just to say that's how it works. Okay, difference of two squares. There's the rule for it. In multiplication, so multiplication is commutative, which means it doesn't matter what order you multiply two things together. So whether you go a minus b times a plus b or a plus b times a minus b, it doesn't matter. But you will always get a squared minus b squared at the end of it. Now, I just want to double check with everybody. Have you, now that I've got it here, have you done this in regular maths? I'm getting a couple of nods. I'm hoping that's indicative of everybody. Okay, I won't belabor it too much. Again, I'll just spell it out very quickly just to confirm we know what we're doing. So I square the first term, which is 3, and I square the second term, which is 4x. And remember, you're squaring the whole term, not just the number or the variable. And so that would be 9 minus 16x squared. Boom. I'll just zoom out so you can see the whole thing. Anyone got any questions over that? Okay. All of these are expansions. When I say dots, I mean difference of two squares. So the result of expanding will be a difference of two squares. So in mathematics, difference means you got four chances here. Mathematics, difference means subtract. Thank you, whoever said that. So difference means subtract. 2 means 2. Squares means the term is squared. So the result should always be a square minus another square when you're using dots. So 3 minus 4x and 4x plus 3. Now, those terms are in a different order, which normally would be a no-no, but I can reorder an addition. So I can go 3 plus 4x, and therefore that would be a dots problem. It'd be 3 squared minus 4x all squared. Same as we did on the left there. The next one is 6 plus 8y, 3 minus 4y. It's not a dots problem because it's not a minus b times a plus b, but if I factorize, I will get there. So if I take out a common factor of 2, I'm just rushing this because I'm conscious that we've done similar things with perfect square. So if I take 2 outside the bracket, I will get 3 plus 4y times 3 minus 4y, which is a dots. Yeah. Dots, difference of two squares. Yep. Sorry, I wasn't speaking to you slowly because I thought you were stupid or something like that. I was just spelling out the DOTS. Yeah, difference of two squares. I've got it written up there. At the top there. Yep. I'll leave it zoomed out. I hope you can read it okay. 4n minus 3, 3 plus 4n. I don't know why I've got that there. That's no harder than the other one, is it? You could even do this though. I could take a negative outside the bracket and I would end up with minus 4n instead of positive 4n in the front one. And instead of 3, minus 3, I'd end up with 3. So I could even do it that way if I wanted to. If I wanted to. I'd rather just reorder the second one, but I'm just saying you could do that. 5 plus a minus b, 5 minus a plus b. Again, it's 3 terms, but you can do something about it. So have a look at this. If I go let x equal a minus b, then I'll have 5 plus x and then 5 minus, hang on, would I have 5 minus x though? So I've got a plus b there, right? Can everyone see the problem? Oh, that's 2. I don't have to zoom up, I'm going to have to. Can everyone see the problem there? I've let x equal a minus b to use that same sort of technique as I did last time. But I've got an a minus b and an a plus b. So look at the line above. I've got 5 plus a minus b. Now, if I go 5 minus and do brackets like this, 5 minus what will give me minus a? 5 minus a. And minus times what will give me positive b? Well, that would be minus b. So the positive b becomes a minus when I put it in brackets effectively. So now I've got 5 plus x, 5 minus x, which is then difference of 2 squares. 5 squared minus x squared. This is just a zoomy zoom thing because I won't be free to help you out on Thursday. Okay, so that's just, so I guess the key thing here in slide 8 then is you need to get really good at looking at a problem and seeing whether it directly fits a difference of 2 squares or a perfect square, or whether you can manipulate it, change it so that it fits a difference of 2 squares or a perfect square. Does that make sense? It doesn't make sense. Is it perfect squares you haven't done? Okay, you've done them now. That's basically it. You're just following the rule. I won't go through why it works, so I don't have time. So I'll just give you this one hard one here, and it is a perfect square. So if you haven't done perfect square, here's another example. So I'm throwing you straight into the deep end with some hard ones here. So we've got 2x squared plus 1 all squared is the problem. So what we do is we end up squaring the first term. So I'll just do it slowly again by putting the first term in a square there. It's plus 1, so I put a plus here, and then I go 2 multiplied by the first term, which is 2x squared, multiplied by the second term, which is 1, and then I finish with a 1 squared. Now, the only thing I need to fix here is that there's a 2 squared, which is 4, and then what happens if I square a square? What's x squared squared? Anyone know? It'd be x squared times x squared, right? Which would be x times x times x times x. So it would be x to the power of 4. Okay? I'm not getting much back from you guys, and because you're wearing masks, I'm stuck between, am I going too fast, am I going too slow, or are you just a really quiet class that won't tell me things? So please tell me if I'm going too fast or too slow. I really need it. The middle one should be straightforward. 2 times 2 is 4 times 1 is 4, x squared, and then 1 squared is 1. So we end up with 4x to the power of 4 plus 4x squared plus 1. Yeah? Okay. So I'll stop the video here, but the worksheet I'm about to hand out in class, I'll also put on Google Classroom, and the worksheet is to be completed next lesson, including the textbook work that I've got here as well. So I'll pause this first.